Let's just dive right into it. Welcome to the incredibly high-stakes world of offshore drilling. Today, we're focusing on what is arguably the single most critical safety discipline in the entire industry, well control. If you've ever found yourself wondering exactly how engineers manage to safely tap into pressurized reservoirs buried miles beneath the ocean floor without causing a massive disaster, well, you're in the right place. We're going to unpack the ultimate mechanical fail-safes designed to prevent those absolute worst-case scenarios.
Think about this staggering scenario for a second. How do you plug a hole in the ocean floor that is erupting with literally 15,000 pounds per square inch of explosive pressure? We're not just digging a hole in the dirt here, right? We are dealing with literal life-or-death realities in extreme deep-water environments. Because when you drill down into a hydrocarbon reservoir, those trapped gases and fluids desperately want to rush to the surface. Keeping that from happening in an uncontrolled, violent way is basically the entire foundation of offshore well safety.
So here's our roadmap for this explainer. First, the threat of a blowout. Second, the first warning sign, known as the kick. Third, the blowout preventer stack. Fourth, regaining control. Fifth, we'll look at deepwater horizon. And finally, modern safety rules.
All right, part one, the threat of a blowout, the sealed pressure vessel.
To truly grasp well control, you really have to shift how you view an offshore well. It's not just a pipe. Think of it as a highly engineered pressure vessel trying to hold back immense geological forces. And if it fails, you get a blowout, a rapid, uncontrolled release of oil, gas, or solids. But why does that actually happen? Well, normally drillers use this heavy, specially formulated drilling mud. They pump it down the drill string, filling the well bore. This mud acts like a giant, heavy, liquid lid. The downward pressure of this mud, the hydrostatic head, has to perfectly balance and overcome the upward pressure of the formation fluids. If that heavy liquid lid fails, or if it just isn't heavy enough, those formation fluids violently push their way up. Blowouts are rare for sure, but they are absolutely among the most catastrophic events in the industry.
Section 2. First warning, the kick.
Now, blowouts rarely happen completely out of the blue. So how do crews actually detect a dangerous pressure imbalance before disaster strikes? The crucial red alert warning sign is what's called a kick. Basically, the unwanted entry of formation fluids into the wellbore. Recognizing a kick early is absolutely critical, and crews are constantly watching for 4 primary indicators. First up is a pit gain. This is when the mud pits on the rig suddenly start filling up because formation fluid is flowing in down below and literally displacing the mud out of the hole. Second is a drilling break. That's a sudden, unexpected jump in how fast the drill bit is cutting through the rock, which usually means they've just hit a highly permeable, pressurized zone. Third is a flow check. If they shut the mud pumps off, but the well continues to flow upward on its own, formation fluid is pushing up. You've got a kick. And finally, seeing increased gas concentrations in the mud returning to the surface. When literally any of these indicators appear, the driller immediately initiates well control procedures. They shut in the well by closing the blowout preventers and instantly notify the tool pusher and the company man.
Moving to Section 3, the blowout preventer, or BOP stack.
So, when that kick occurs, the crew relies on their ultimate mechanical fail-safe. Just look at the sheer scale of what we're talking about here. A subsea blowout preventer, used on semi-submersible drilling rigs, is a massive towering assembly of steel that actually rests right on the ocean floor at the wellhead, not up on the drill floor. It sits beneath the marine riser that connects it to the rig. And it's controlled all the way from the surface via 2 independent control pods, one hydraulic and one electro-hydraulic. This entire behemoth is basically our absolute last line of defense against the explosive pressure of the Earth.
If we look inside, at the very top of the BOP stack, you'll usually find the annular BOP. Internally, this thing uses a massive, heavily reinforced rubber packing element. When it's activated hydraulically, this giant rubber donut basically flexes and constricts, creating a super tight seal around whatever drill pipe happens to be in the hole at that exact moment.
Let's compare the tools inside the stack. On one hand, you have those annular BOPs at the top. They are incredibly flexible. Because of that rubber seal, they can adapt to different pipe diameters or even close on a completely empty hole. But they generally can't withstand the absolute most extreme high pressures. That's where the ram-type BOPs come in. Positioned below the annulars, these are the heavy hitters. We're talking brute, high-pressure containment. They're basically massive steel blocks that shoot inward from the sides with immense force to seal, grip, or even completely sever the pipe.
And there are a few specific flavors of these ram blocks. You've got pipe rams, which are perfectly shaped to close around a very specific size of drill pipe, Variable rams can handle a small range of sizes. Blind rams are just flat, solid steel blocks that smash together to seal the wellbore if there's no pipe in the hole at all. But the really critical ones are the blind/shear rams. If everything else fails, or if a rig suddenly needs to disconnect because, say, a huge storm is rolling in, these rams have hardened cutting edges. They are designed to literally slice right through the heavy steel drill string like butter and seal off that extreme well pressure below.
All right, Section 4, regaining control of the well. Okay, so the crew has detected a kick, they fired the BOP, and all that explosive pressure is now trapped safely below the seabed. What happens next? Well, we enter the well kill operation. Step 1, like we just said, is shutting in the well. Step 2 and 3 utilize special high-pressure pipes running right alongside the BOP stack and up the riser, connecting to manifolds on the surface. These are called the choke and kill lines. First, they use the choke line. This allows them to carefully bleed the explosive kick fluid out of the well in a controlled way while the BOPs remain closed. At the exact same time for Step 3, they pump a specially formulated, much heavier drilling mud down the kill line all the way to the bottom. This heavier mud slowly displaces that lighter kick fluid, gradually increasing the mud weight until it overbalances the formation pressure. Basically, they reestablish that heavy liquid lid and restore safe hydrostatic balance.
Section 5, the Deepwater Horizon Disaster.
We really have to anchor all of this engineering theory in a very tragic reality. Let's look at the blowout of the Macondo well in the Gulf of Mexico on April 20th, 2010. Investigators uncovered a devastating, almost unbelievable cascade of human and mechanical errors here. First, a critical negative pressure test to check the well's cement seal showed over 1,400 psi of pressure on the drill string. That number should have been 0. Inexplicably, the tool pusher and driller misread this anomaly, brushing it off as some non-existent thing they called a bladder effect. Shortly after, the cement shoe at the base of the well failed, letting oil and gas rush in. Mudloggers who were supposed to be watching the fluid returns completely missed the increased flow for a critical half hour. Once the blowout hit the surface, the crew made a fatal choice. Instead of diverting that explosive gas and mud safely overboard, they routed it into the rig's mud separator. It was instantly overwhelmed. The gas flooded the rig, found an ignition source in the engine room, and caused a massive explosion. And tragically, as the investigation showed, the subsea BOP control systems had to be rigorously maintained. But here, they had faulty systems, and the ultimate failsafe completely failed to seal the well automatically.
33 hours. That is how long it took after the explosion to finally force that faulty BOP partially closed using an underwater remote-operated vehicle, or ROV. This failure was just catastrophic. It cost 11 lives, sank the Deepwater Horizon, and caused one of the worst environmental disasters in history. The investigation was incredibly clear. While better technical solutions absolutely existed, it was human error and severe management failures in assessing risks and maintaining equipment that were primarily to blame.
Which brings us to our final section, number 6, modern post-Macondo safety rules.
To make sure a nightmare cascade of failures like Macondo never happens again, sweeping regulatory changes completely overhauled the industry. Regulators mandated massive hardware improvements. Rigs must now have dual shear rams, so 2 sets instead of 1, giving them critical mechanical redundancy just in case the first set fails to cut the pipe. They also require an independent acoustic emergency control. This acts as a backup, letting operators trigger the BOP using sound waves through the water if the physical control cables get severed. Plus, they added automated triggers. The deadman function automatically closes the BOPs if all hydraulic pressure and communication is suddenly lost. And the auto-shear function automatically shears the pipe and seals the well if the drill string goes slack, like if the rig's somehow disconnected from the riser.
But listen, hardware is literally only as good as its maintenance, right? So BOP testing is now governed by incredibly stringent rules. Every single ram must be function tested regularly during a well operation, typically every 14 days at a minimum. The entire BOP stack also undergoes rigorous pressure testing. They do low-pressure tests around 200 to 300 psi just to check for subtle leaks, and high-pressure containment testing up to 70% of its rated working pressure to confirm it can actually hold back the earth. Operators have to keep meticulous records of all these tests, which are verified by independent inspectors.
I want to leave you with this incredibly stark quote, straight from our source material. A poorly maintained or untested BOP is a regulatory violation, and a potentially fatal one. The engineering behind deepwater drilling is honestly miraculous. It operates right on the razor's edge of extreme physics, just to keep our modern civilization powered. But it begs a really important question for all of us. As our global energy demands push us into deeper, increasingly volatile oceans, will our mechanical fail-safes and human oversight truly always be enough to keep the Earth's most violent forces contained?